Yeah, please proceed.
Yes. Hi, my name is Kim. I'm starting the master's program in math at Texas State University this coming fall semester. So today, I'm sorry. I'm sorry. So today I'm gonna give you the big picture of my paper. So which is about the Calvi-Yau theorem on Riemann surfaces. So there are three approaches, and the first one is elliptic, and the second one is parabolic, and the third one is stochastic. So today, I'm gonna just give you a brief introduction about the first one and the first approaches, which is elliptic approach. So the elliptic approach is make the complex Monge-Ampere equation reduced to a linear Poisson equation. So the thing is that the general Calvi-Yau theorem is usually non-linear elliptic problem, but in complex is going to be the linear elliptic problem. And what is the Monge-Ampere equation? So in complex dimension n, this is the Monge-Ampere equation. So omega naught plus I partial d bar, and the phi to the n is e to the f, and omega naught to the n. When n is equal to 1, and this is going to be the Monge-Ampere equation, and this is going to be the equivalent to a Poisson equation for the unknown potential phi, which is real valued function, scalar function. So today's goal is I like to connect in the Gaussian curvature to a Laplacian type Poisson equation. So I have two examples. The first one is unit sphere, and the second one is the flat torus. So let's look at some background knowledge. So what is the regular surfaces? So let S in R3 be a regular surfaces. Then we have the parameterization u v and to the x u v. In this case, xu and xv is not equal to 0, which means these tangent vectors are linearly independent. And what are the fundamental forms? There are two forms. And the first one is literally first fundamental form is defined as this: e to the du square, f du dv, and g dv square. So we define E as the inner product xu, f, and g as follows. And this is the second fundamental form, and we use this metric. And in this case, we need a unit normal vector, so we can find the unit normal vector in this expression. And the next one is the shape operator. The shape operator is defined as like this way, and the sign is negative. This is for every tangent vector W. So in the coordinate basis xu, xv, in the matrix of S is represented by I inverse times, first fundamental form inverse and second fundamental forms of multiplication. So whereas the first fundamental form is matrix like EFFG, and the second fundamental form is EFFG. So how can you find the Gaussian curvature using the shape operator? So we can find the Gaussian curvature in the determinant of the shape operator. The shape operator is defined as like this way. So this is going to be the denominator, and this is going to be the numerator. So the Gaussian curvature is second fundamental determinant of the second fundamental form divided by determinant of I inverse. But I'm sorry, divided by determinant of first fundamental form. So the orthogonal coordinate curvature formula. So this is the Gaussian curvature using the shape operator, and we're gonna take a look at what is gonna be in the orthogonal coordinate system. So suppose the coordinates are orthogonal. So the coordinates are orthogonal, so this inner product is going to be 0. So which means they're orthogonal, so f is going to be 0. Then first fundamental form, this term is going to be canceled, so it's going to be e du squared and g dv squared. Then we can define a squared, e as a squared and g as b squared. That is, a squared is inner product of xu, b squared is xv. So in this case, the Gaussian curvature using the shape operator, this is going to be f was 0. So the denominator is just eg. And we set e as a squared and g as b squared. So the denominator is a squared and the b squared. The numerator didn't change. So we need to express numerator, which is the second fundamental form, in terms of only determinant of second fundamental form, in terms of only a and b or their derivatives. Since these are orthogonal each other, the unit normal vector, so xu and xv is literally perpendicular orthogonal to each other. So in this denominator means the area of parallelogram, which means it's just a rectangle. So it's going to be just multiplication a times by b. And then we need to decompose the second derivatives as follows, like this way: uu and uv partial derivatives and the vv. So we need to set the coefficients like this way: alpha beta, gamma theta, and sigma tau. And this one is just EFGN. And we need to find these coefficients in terms of A and B. So let's take a look at the first one, XUU. So we can use the inner product property. So we define E as A squared. So this is E. So this equals A squared. So if you take a partial derivative with respect to U, then it's going to be like this way and this way, but this is the same. So cancel out on the both sides. We have this inner product xuu, and xu is a times a with a partial u. So xuu was like this expression. So we can just solve this system of equation. So this one is xuu is like this way. We can substitute into this inner product. So this is going to be alpha. We can factor out in product xu, and b, and as follows. But in here, this is orthogonal coordinate system. So which means this is going to be 0, and this is going to be 0. This is going to be canceled. So it becomes alpha a squared. So this is the same. These are the same. So a partial u is alpha a squared. So therefore, alpha is a partial u divided by a. So similarly, we can find other coefficients like this way, but the computation was too long and complicated. And so I just omitted, and we can use the commutativity of partial derivatives like xuuv is xuvu. So we can solve the system of equations. So consequently,
So there's a question.
yes.
The screen.
I'm sorry.
What does X mean in the notation X, U, X, XV? Can you scroll up higher?
Oh, I'm sorry. One moment, please. Just. I'm sorry. Today is the first time I'm using the screen share, not the whiteboard. So please bear with me. Yeah. Oh, yeah. I'm sorry. So what was your question again?
Can you scroll? Can you scroll? Stop.
Yeah.
N equals. What does the numerator mean?
No, this one. This is
Yes.
tangent vector.
Okay.
Yes. In the direction of u and the direction of v, the partial derivatives.
Might be
And
better
their
to show
cross
the
product.
concrete example.
I'm sorry.
It might be better to show the concrete example, what each of them is in the setting.
Yes, I'm going to show you an example at the later.
I'm just talk about the numerator.
Yeah.
Yeah, just the form concretely. Yep.
Yeah.
I'm just talking about the explicit form of the coordinate in S2, then show the form of the capital X, and just show the X of U, X of B, and cross product. So just that part.
Okay, let's skip to the S2 then. So we're going to see the calculation here. So in a unit sphere, we're going to use a stereographic parameterization. So as you know, unit square is defined as follows. And then we're going to remove the north pole. And then we have the parameterization, this in R3. So in here, we need to find the normal vector. So the first, I'm sorry, not the normal vector. So this is the parameterization. The denominator, as you see, 1 plus u squared and the v squared, they're the same. So I'm gonna set this to the d. So this one becomes like this way. Then x partial u is just, we need to find the derivative using the quotient rule. Then just differentiate with respect to u. And then d was 1 plus u squared plus v squared. So we use the quotient rule. So this one is the square of denominator, and the u, the partial u of E2v is 0. And then minus 2v, and the the partial derivative of u squared is 2u. So this component becomes negative minus 4uv divided by d squared. So in this parameterization, xu, xv means simply partial derivative with respect to u and with respect v. But in this case, this is a little bit different because I just set this d as 1 plus u squared v squared, but you don't have to do it, yes. So does this answer your question?
Karen, is that clarify your question?
Yeah, I just wanted to know notation. Thank you.
Thank you. Oh,
Yeah, you can go back. Yeah,
okay,
thanks.
yes. So after calculation, we obtain the second determinant of a second fundamental form is as follows. And the Gaussian curvature was defined as this. So EG minus F squared is numerator. So K times A squared, B squared, and denominator is going to be like this in negative AB, and we obtain this formula. So this formula is in the orthogonal coordinate system. So this star equation, we got to remember this equation. And what is the Poisson equation? So in conformal coordinates, so conformal means A and B, and they are the same, which means earlier E was A squared and G was B squared. So if A and B, if they are the same, then E and G are the same, which means this and this gonna be the same. This means conformal. So in conformal systems, A and B same, and we gonna set E to the phi. Then by the chain rule, we can get a partial derivative. So B partial U is like this way, dot, 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 dot. And A times V, so partial of E to the phi, then it's gonna be the chain rule, E to the phi times phi, partial V. This is gonna be B times phi partial V. And then A partial V over B is phi partial V. Sorry, yeah. So you're gonna substitute these value into the star equation in here because we found this one, all right? So after that, we can find the Gaussian formula, Gaussian curvature in this way. So this becomes like this way. So after that, we're gonna get this conclusion. The Gaussian curvature is equal to negative e to the negative 2 times phi times Laplacian of phi. Equivalently, this is gonna be negative e to the negative phi. So negative Laplacian of phi is k, which is Gaussian curvature times e to the 2 phi. So this is the Poisson equation. So we can find the Gaussian curvature in the Poisson equation. So let's take a look at the example. We already saw this S2, this part before. So I'm gonna proceed, continue the rest part. So let's take a look at this first. In this parameterization, x coordinate, y coordinate, and z coordinate, the numerator is different. But denominator, they were all the same. And this x component and y component, just only u and v So this is symmetry, and the z component is 1 minus 2 over d. So it doesn't depend on u nor v. So by symmetry, in here, this one, if x partial u, then negative u square. If x partial v, then negative v square. So this y component becomes x component. The z component is going to be the same. So by symmetry, we easily know that inner product xu is equal to xv and xb. So the large E is 1 over d to the 4 and the term is too long. So 4 times 1 minus u squared plus v squared, the square plus 16 u squared v squared plus 16 u squared. And then we can factor out 4. So and we can expand this one. And after some calculation, so minus 2u squared plus 4u squared becomes 2u squared. Minus 2u squared v squared plus 4 times u squared v squared becomes 2u squared v squared and plus 2v squared. So this part, this is just a complete squared, 1 plus u squared plus v squared. So this becomes, this gonna be canceled because d is 1 plus u squared plus v squared. So cancel, then we have this one as g. So in a unit sphere, u and v are just orthogonal coordinates because we just use like xy plane. So f is 0. Thus, the first fundamental form or this metric is going to be 0. So like this way. So this was conformal system. Oh, I'm sorry, this was typo. It was e to the square. So we can factor out 4 over 1 plus u squared plus v squared square and du squared plus dv squared. And then the first fundamental form I is 1 e to the 2 phi du and dv. So we can solve this system equation. We're gonna get this one. E to the phi is 2 over 1 plus u squared plus v squared. Therefore, the real value scalar function phi is equal to ln2 minus ln of 1 plus u squared plus v squared, which is natural logarithm. So observe that the partial derivatives of phi, so partial derivative of phi with respect to u, so I believe we can find this value using the quotient law. And the Laplacian is defined as this one, this second derivative, partial derivatives. So we can just substitute these values into this, then we have this result. Therefore,
I have a question.
yes.
I remember that if you add them, then the second term how to ah I see. Is
Oh,
to
yeah. This part,
yes.
yes. So you can just u square plus v square, but the denominator was square, right? So if you just yes. So you can make the common denominator. So for this one square and this square, yeah. So you're gonna get this value. Or you can just plus 1 minus 1. So anyway, so the Gaussian curvature via the Poisson equation. So Laplacian of phi was negative e to the 2 phi. So this is going to be cancel each other. So the Gaussian curvature of unit sphere S2, we obtained 1. So the second example is flat torus. So with the parameterization,
This is not
we
flat torus. You shouldn't call it by embedded torus. Those are
oh
two very different like the objects.
oh I'm sorry, I didn't know that. Okay. So I'm sorry, one more. Oh, can you repeat one more time?
Usually this would be called by the embedded torus, not the flat torus.
Ah,
Flat torus is completely different one.
okay. Oh, the torus is embedded in R3. Is this correct? Okay. Or so is that also denoted as T2? Is this part? Oh, correct. Oh, thank you. So we have this parameterization of torus. Then we have this like computation. You can see it later. And we have f as 0. You can just compute it, or we can just think it in geometry way. So like this torus was like, so this angle is V, and this angle is I defined as U. So this poloidal angle is U, and this toroidal angle is V. In here, if you just think about it, that in here is already perpendicular each other. It's orthogonal. So we don't need to compute this part. So we can think of this way too. And the last term, the G was xv dot xv is like this way. And the metric was like f was 0, so like this one. But if you look at this here, we have a problem. In here, A is R. And B is R plus R cosine U. Because we defined A was E squared, yeah. Then, this case, A is not the same as B. So, okay, let's keep that in mind. And I'm going to substitute into the star equation. If you remember this one is Gaussian curvature in orthogonal coordinate system. So you're going to substitute this into this way, right? And then do some computation. We have this Gaussian curvature. But if you take a look at this, note that this Gaussian curvature was this Gaussian curvature depends on U, not V. So I'm going to rewrite as Gaussian curvature as K of U. So since E or A squared, R squared, so E and G, they are different. So it is orthogonal but not conformal. So this coordinate system is not conformal, but orthogonal. So in this case, we're gonna need to introduce a new coordinate, u tilde, like this way. So we can make that conformal. So we want this one is gonna be this way. So we can solve this equation. So du r square du square and dv square. So dv square is going to be just cancel. So this is going to be like this way. And we have this result. So in this new coordinate system, the metric is like this way because this is conformal. Then we have this. Oh, yes. So I was e to the 2 phi of tilde u, so this one. Then, therefore, the Laplacian of tilde u is log of r plus r cosine u and then u tilde. So it is conformal. We have this one. We have this equation. So since phi depends only u tilde, so this Laplacian, the second partial derivative of with respect to v of phi is going to be 0. So we can get a partial derivative of phi with respect to u, and we can get this one. We can take a reciprocal. So using the chain rule again, we have this Laplacian. So we're going to substitute this and this one into the Gaussian curvature in Poisson equation. Then we have a Gaussian curvature as the same as the earlier. So to summarize this whole process, so if you have just a regular surface, then we're gonna find the first fundamental form and the metric, and we're gonna check if this coordinate is conformal or not. So if it was conformal, then you can use this one. If not, we can introduce new coordinate variable like this way. So this is it for today, and thank you for your time.
Yeah, very well done in terms of the concrete computations with drilling with depth. So, for Ujun, I have two questions for
Yes.
the learning procedure.
Yes.
One is, so what's the point of doing this computation? What is the goal in your understanding? That's first question. The second question is, so in terms of learning, through the procedure of preparation of this presentation, what did you really genuinely learn?
So as far as I understand, I just have a just glimpse about the first approach, which is elliptic approach. So I learned that we found the Gaussian curvature in this original way using the determinant of shape operator, but we can connect or we can express that Gaussian curvature using Laplacian type Poisson equation. So if the coordinate system was orthogonal and conformal, then it'll be no problem. But yeah, if it's not conformal, then we need to make it conformal. And so we can express Gaussian curvature in Poisson equation. So that's what I learned. And what was the second question? Sorry.
So through the preparation, what
네.
did you really learn? I'm not talking about the mathematical contents, but
Oh, yes.
kind of the spirit.
Just like without thinking, I mean, I think the computation without thinking is useless. So if you just do just a really basic computational calculation, you need to just, I need to just think about it. Is there any another way, or is there any interpretation? Like I found like this way, or yes, anything else? And the computation is the key to understand the concept or some theorems or everything. So in this process, I didn't just like saw and wrote it down repeatedly. You know what I mean? So I just do it. I just try to do it my own way. In that process, I just pick up some new things, and also in that process, I found that which part was I was confused about, and this helps me to improve my understanding about this concept, even though I'm not 100% sure for that I'm the understand this concept, but yeah. Anyway, but I have a little bit gist of it, and I have a little bit confidence that okay, I can do it like this way for the rest of my master's semester.
And so before we move on to the discussion regarding what Wu presented, I want to point out the core of the computation together. So the key reason is, so we start from geometry. So the geometry part, so the Gaussian curvature has a very like the depth implication in many ways. And later on, when we all together learn the language of Riemannian geometry, we will see the importance of the Gaussian curvature as realizations as either the sectional curvature or the Lich curvature or the scalar curvature or in complex geometry as a holomorphic sectional curvature and so on. So, but for a moment, the point of doing this computation is, so from the Gaussian curvature, so what Wu did is he derived the certain equation as he pointed out as a Poisson equation. Then once we reach out this like the output, so that the input was the Gaussian curvature, and by just using calculus, so that he derived this PDE. So once we get this PDE, we can reverse the relation between input and the output. So the previously, if you just show the like the general framework of the converting the Gaussian curvature to Poisson equation, can you just show that one? I mean, in the general one, not the example. Yeah, here. So yeah, probably this page should be good. So that the overall, so we start from the definition of the Gaussian curvature that has a significant meaning many ways. Then by using calculus, so that he derived this equation. Then one can ask the reverse implication. Then why don't we start from this PDE? Then now we have a PDE. As long as we have a differential equation, we can ask first, is there a solution? But from this procedure, we actually already know there is a solution because we start from the solution in the first place. But if we just have this like the PDE, then we can use adopt the modern technology of the PDE theory to get the first there is a solution, and if the solution exists, then is that unique? And how can we control the select solution from the general point of view of the PDE? Then this turns out to be the same information of the determining the Gaussian curvature. So this is the point. We'd like to reverse the input and the output. So this computation shows how to reverse, how to take the reverse between input and the output in a sense that now we just need to keep the PDE. This is, we will later call by the very first elementary prototype of the Monge-Ampere equation. Then once we have a Monge-Ampere equation, then actually we know the Gaussian curvature. It's kind of convincible, and more on, this is just a prototype. So when it comes to talk about the Monge-Ampere equation with the PDE side, that implies the geometric structure. Then This is we call the Calabi-Yau theorem that we will see all together later on. So the compact Riemann surface, especially with the S2 and the torus, the two-dimensional torus, is the simplest possible case that in a sense that we can if we see this all observation as explicit as possible. Then once we establish this observation from the elementary calculus point of view, then we can see how that abstraction really works. This is a whole point of doing this procedure. So the way of the learning the PD theory from this perspective is that then we first need to catch up which like the tools of the PD theory should like available. For example, the maximum principle, subalem inequality, like the Nash embedding, or and so on. Then not just catch up the general knowledge, we will see what was really going on in this like the sphere and the torus setting, because in this setting we know everything already. Then we can really catch out, this was what this like the abstract framework is talking about. Then we can really understood what was going on behind. Then in that sense, we can see how we can like the twist the setting a little bit in our own context to do our own like the research. So this is the reason that all today's the core of the today's computation was that Wu didn't use any fact. He just proceed the elementary calculus to derive the Poisson equation. Once we get the Poisson equation, then we can study geometry in terms of the PD techniques. This is the one like the core, so that the as Wu pointed out, so the rest of his like the not just the rest, so his like the master period would just completely fill in terms of these types of the elementary calculus, but the implication is never simple. It's not trivial. But on one hand, so I wanna learn all of the participants here that learning advanced level of mathematics is not catch up the textbook. It's not studying the GTM series. Of course, we need to look at those like the advanced like the topics, and we need to digest the important topics as detailed as possible. That's for sure. We definitely should know it at some point, but it's not as just taking the coursework. We first need to look at the very elementary computation, and then once we understood what was going on behind, then the theory, we kind of get this sense of what was going on, then we can move on. And if those some of the details are really needed, then we really need to do everything in detail, but not as just read the like the chapter 1, chapter 2, chapter 3. It's not like that. This is the way of doing the advanced level of the learning mathematics. This is one point. And there's another point I want to mention. But before I mention that, like the mathematical contents, is there any comments or questions regarding the mathematical contents that we presented? Later on, the all computation here, I will require all of the graduate students to know how to do it. So if there is no other question, let me share my screen to explain the further implication, not just directly the research direction of U, but it connects all of your like the research interest that I want each of you to develop in the different like the disciplines. So let me share my screen. Yeah, so this is the like the file that I made while I listen U's presentation. So Wu concerns Monge-Ampere equation through his master period, so that so from this seminar, you will see all of the very detail with the depth of the learning Monge-Ampere equation. Focal length equation is related to the SDE side that Tae is presenting nowadays a lot. And the Hamilton-Jacobi-Bellman equation is coming from the dynamic programming, also coming from the stochastic part that I will ask Hejin to present very soon. So even these three PDs have different like the context, but in fact they are the same. So what I want to point out, and what Andy will present later, is by using the maximum principle in the setting of the generic Taylor manifold, so that how we establish the Schwarz lemma. And then again, we will also replace that context. So in the like the probabilistic stochastic like a context later on. So when it comes to talk about the Monge equation, I will not just explain everything in detail. So I just want to point it out that so for example, all of you know the standard Gaussian density that satisfy the standard heat equation. And this is also a key part of the Brownian motion also as well. And then we'd like to transfer the density from this initial state to the another one. Then the Fokker-Planck equation explains how to transfer from one to the other in terms of the space of the densities. And this first perspective can be changed in terms of the optimal transfer, which is purely applied like the side and also geometric analysis side, so that this can be also interpreted in terms of the so-called finite, like the composition of the transport map. And also there's a interpretation of the Fokker-Planck equation in terms of the SDE. So that those three objects are, in my perspective, essentially the same information, but with a different like the angle and the description. So as we did today, I invite any of the participants eventually just go over this computation with the depth, and then you will concretely catch up why those are like correspondence from one to the other. Then you can definitely see. So even for example, so who is talking about the Monge-Ampere equation, then you can interpret that context in your own context, even though those looks completely different. This is the way to learn mathematics. Is that kind of okay with it? So in order to do it, we first need to see in the simplest possible, like the elementary example, you know how to establish a correspondence in your own way. This is the reason that I try to invite to this type of computation so that you can look at this one. And also it matters to look at the CP one and also the torus as we did today. Of course, he just look at the like the real torus for a moment, but eventually it will be converted as a complex torus. So that I will post this like the note so that I invite you to also look at this computation and give the presentation. And we need to look at not only Monge-Ampere equation from this seminar, but also we need to look at the Fokker-Planck equation. You will encounter this a lot from these seminars as well. But when it comes to talk about the Hamilton-Jacobi-Bellman equation, this is what I am currently working on with Hejin for Hejin's PhD project, so that you will also see from drilling the certain necessary like the computation together. So what is the meaning of the Hamilton-Jacobi equation coming from the Lagrange multiplier like the method, and then we will see how those are also connected. So please do not like try to catch up all necessary like, knowledge, but just look at your own example, and as long as you know the correspondence, then actually you have your own like the sense of how to develop anything further. That's how we proceed the research. So this is the core part of I wanna explain to especially you, in a sense that in this way we can catch up our advanced knowledge in the like the within the decent amount of time, not just spend around a decade to catch up all necessary techniques. So before we move on to the next presentation, any comments or questions? I will put this like the note into the regular seminar tab. Any comments? So I want to invite you, by the way, so after all, so you should think about this way. So if you have have already intuition about the Gaussian curvature, so that you'd like to take the benefit of the usage of the explain what is the geometric intuition of the Gaussian curvature, what is the geometry like the meaning of it, that matters a lot. But at the same time, you'd like to use that into your own mathematical research. But how that really works, then you need to find the connection between your intuition and the real way of the usage of the modern technology. At least there should be a bridge with the calculus and linear algebraic computation. So in order to do it, you should know, for example, as we did today, so that once we have the intuition about Gaussian curvature, so it just explains the geometry like the structure, then once you convert it as an equation, then you know how to handle, mathematically speaking. Then you can do the research so that you can just do the certain types of the computation. Then you can claim this really like is the decent like the way to justify this structure really works in your algorithm. And this is the way to develop the new types, new like the extension of the classes of the doing research in the pure mathematics and so on. So in order to do it, you need to connect. So especially how do we reduce the mathematical objects that you can handle in terms of calculus and linear algebra? So now you have a tools, but not just as using the Monge-Ampere equation as would you should do, you also have your own like perspective. For example, so from learning Riemannian geometry language very soon, so I will ask Andy to establish so-called the Chen-Lu formula. Chen-Lu formula is the standard way of establishing Schwarz lemma of Kähler manifold. This is the two like the different like the combination of the objects. One is the Poisson type equation, as we'll drive today, and another one is so-called the maximum principle. So those two are the major pieces of the established Schwarz lemma. But and in order to control that Schwarz lemma via the Chen-Lu formula, so the Lich curvature lower bound plays a role. So that we should see how the Lich curvature play a role and how do we establish this like the standard one. But the point is we can replace the maximum principle. This is the whole point. So that as long as we are able to replace the maximum principle, and the one of the reason in the pure mathematical like the side of the context to replace why we should do that. So the in the geometric analysis or the differential geometry. So in order to apply the maximum principle, there should be so-called the elliptic operator, and the Laplacian is such a like the example. Laplacian is satisfy the ellipticity, and the elliptic operator we can use the maximum principle. But when it comes to weaken the assumption to the second order differential operator, this might not be the elliptic operator in general. So there are few important terms such as hypoelliptic operator or the subelliptic operator and so on. The key reason to replace the geometric analysis techniques to the probability theory is that we do not actually need to require the elliptic operator to apply to get the maximum principle. So the maximum principle does not require the ellipticity in the stochastic like the theory. This is the reason that so if you want to weaken the setting from the known setting of the geometric analysis to the more like the general classes, then we should like the weaken the assumption of this like the operator that we eventually should rely on establish the inequality based on the maximum principle. But in order to do it, we should use the theory that works with the maximum principle with this like the weakened setting. Then the stochastic like the framework will provide such a like the way. This is my own reason. And also this could be also important to later connect to the like the more applied context so that you can actually do any types of the research after all. So this is also my own reason. So yeah, any other comments or questions including you? Yeah, if not, then we have a next speaker.
Can I share my screen? Okay. Before the beginning, I have one thing to ask for understanding. Uh, I am putting my 2 years old son on my knee because I failed to make him sleep, and it's all my fault. So some noises could be mixed with the sound. I'm sorry about that. Okay. Okay. Before the beginning, uh, I should mention that I invest several times to bridge between the differential equations and the stochastic methods. So this ti- this seminar is also on the same route. I bring the Schwarz lemma, alternative proof of the Schwarz lemma, which is covered by Andy already, because it could make you interested. So let's start. And the in this proof, we prove the search lemma through the maximum modulus principle, and it was derived from the open mapping theorem. I will introduce the alternative way. It is essentially the special case of the maximum modulus theorem, but it could be derived derived through the probabilistic method. I'm sorry. Okay.
So nowadays, Haru, my first like the son, always takes my iPad during I present something. So it's hard to get mad, but yeah, I don't know.
Sorry about that. Okay. The setting is same as the and this f from the unit disk to unit disk, and suppose that to 0 is 0, and we will prove the these trees. First, we will define the accelerate function g as the same as the and this, like this. Because g is a holomorphic, it should be follow the Cauchy-Riemann equation. So we can see the G should be a harmonic in Euclidean sense. And I introduced that I mentioned that the operator can be translated into the language of the diffusion, and the Laplacian, in the case of the Laplacian, it was exactly the Brownian motion. So we will define the 2D Brownian motion, and we will introduce a step how R, which is called the so-called stopping time, but we can easily understand by the time to hit the boundary of at first, and then we will apply it to formula on G. Then we can get this equation. We say the second term to be a martingale part. We will meet it frequently, and this part is called this part. Second term, the expectation of the second term will be 0. It is the most important property of the martingale, and we saw the Laplacian of G is 0, so the liquid part is also 0. So by taking expectation, we get this equation. I should mention one more thing. The G was the harmonic function, so we get the martingale, which result is the like the value at the point is equal to exactly the expectation. For the subharmonic case, which is the Laplacian is larger than 0, then we get sub martingale, which is the case. We can easily this part should be positive. So GG expectation minus some positive. So the the value of the function at a point should be less than expectation. So we can get the inequality from the subharmonic and subharmonicity or harmonicity like this in probability method. We so at the maybe the most important case would be the absolute scale in subharmonic motion, and we will with this inequality frequently. So we get we got here, and then take the absolute value. Then we got this, and this expectation is a kind of the integral. So the absolute value of integral should be less than the integral of the absolute value of integrand. So we can get this inequality. So and then this time is
Yeah, take your time.
this time is time to hit to the boundary. So this value should be the boundary at R. So here would be to be GR, just GR. And we know that GR should be less than 1 over R. So actually, this part is essentially the application of application of the maximum modulus theorem, and this process these steps are these steps are the essential part of the proof of the maximum modulus principle through the probability method. And then when they take the R to be 1, then we get the results of the first and second one. The key point of this root is this, where let's think about like this. G is here, and we set the boundary like this. Boundary to the circle and centered at G, and we built the Brownian 2D Brownian motion at with the starting point G. So the diffusion process process follow the Brownian motion, which is radial symmetry. I'm sorry. So at some time, the process hit the boundary. So each point of the boundary has the probability to hit this boundary first. So, for example, one third. Then we can, and then we have a function g. Then we can calculate the expectation like this. This is this process would determine the value of the function at this point, this center. This is the essential point of this proof. To get the equality case, it is easy in this intuition. Assume the modulus of f is the same to the modulus at the point. Then draw a small circle which is contained the unit disk. Then the Brownian the 2D Brownian motion is the no. This is the highest the maximum value of the function of g because it is 1. And we know that G0 should be expectation of G of boundary. But this is the maximum value. So the values on the boundary should be all the same to be the maximum. And then we adjust the radius of the he select. I'm sorry. So every circle centered at G0 has the value 1. So we can expand this scheme. So we can get the whole domain or whole domain on the disk. So in summary, the essential part is this. the maximum modulus principle give us an inequality using this, and it could be derived from the martingale and stopping time using this equation and the change orders between absolute value and the integration here. And then finally we take the supremum. Then we can easily retrieve the maximum modulus principle through the stochastic method. Where it is end of my presentation today. Have any question or comment? I'm sorry about the noise and happenings.
It's a pleasure to
Oh.
have you. Yeah, looking, please go ahead.
Yeah, I wonder, the condition is condition is important. GG is so romantic.
Uh, I couldn't hear.
This is an alternative proof of maximum principles,
Yes.
and I see what and the proof itself using the uh, uh, the proof. um, I don't know. Anyway, what I have a question. This holomorphic condition is important.
Yes. Sure.
What
Uh,
part you use?
Here.
Yes.
Ito formula gives this equation, and uh, because G is G is holomorphic. This part
Yes.
and this part
Ah.
go to zero automatically by taking the expectation. Or in subharmonic case, this part could not be zero. So the final result would be a inequality, not the equality. And this part could be this part could be viewed as the how can I say it? Gauss's mean value theorem, because as I said, the Brownian motion has the radius symmetry. So we if we set the boundary as the circle centered at the point, then this expectation should be the like this R G, no, actually this R on circle, and this is the it is the Gauss's mean value theorem. It quite it is related to the Cauchy integral formula, I guess. So the proof through the probability method is the uh, proof through the Gauss's inverse.
So let me put some comments of the importance of what take do with this note. So this is really astonishing in by all means, I want to say. So, I want you to get motivated to really look at what Andy did. So, the Schwarz lemma, that the standard way of establishing the contraction property of the holomorphic, any holomorphic map, is coming from, as we said several times even today, maximum modulus principle. And the maximum modulus principle, so the way to apply was the so-called open mapping theorem. And the open mapping theorem, so if you know the definition of the continuous map in the topology level, you know the what is the definition. Any If you take the any open set from the codomain, then the inverse image must be open. So this is the standard definition. Whereas the open mapping says if we take the any open set from the domain, that image becomes open. In general, we cannot expect such a like a property. Then holomorphicity guarantees the open mapping property. And the open mapping property implies the maximum modulus principle. Again, the way to describe from Andy's one of the previous presentation was astonishing in a sense to show how it really works. And actually, I'd like to put one additional comment because I want to reduce all mathematical facts from the elementary calculus point of view. So that open mapping theorem is the magic, and the open mapping theorem is coming from the Cauchy integral formula, and the Cauchy integral formula is coming from the fundamental theorem calculus in the differential form level. So this is, I want you to, at some point, if you have a chance to look at it, so not just knowing the fact, I want you to start from the FTC, fundamental theorem calculus, that yields Cauchy integral formula, that yields open mapping theorem, that yields maximum modulus principle, that yields the contraction property of the unit disk with the any holomorphic function that we call the Schwarz lemma or Schwarz peak lemma. So this opens the understand the structure of the hyperbolic geometry, which is also the structure of the collection of the one-dimensional numerical distribution, and even for the multi-dimensional numerical distribution, it possesses the similar structure from the Kramer-Rao inequality of the information geometry or statistical like the context whatsoever. But I want to point out from this note, you can see that all we use for the holomorphic structure is the harmonic. So from the first, like the page as take it very well, so that because the holomorphicity is equivalent to satisfy the Cauchy-Riemann equation, and the Cauchy-Riemann equation forces the harmonicity. And the harmonicity just means that Laplacian equals zero, and Laplacian equals zero forces the second order term of the Ito formula should be banished. But converse is not true in general. So this is the specialty of the real dimension 2. For real dimension 2 case, holomorphicity is the and harmonicity are actually the same. Holomorphicity implies harmonicity, and conversely, if you start from real harmonic function, then you are able to make it to be the holomorphic. But this is not true from complex dimension 2. So the holomorphic map is much narrower than the class of the harmonic functions. So this argument does not require holomorphicity at all from any of the argument today, rather than just talk about the Cauchy-Riemann equation to force the harmonicity. So harmonicity was sufficient to establish the Schwarz lemma. This is one important point. So that this is established in terms of the weakened like the setting. This is one thing I want to mention. So second, this is also important. And when it now comes to talk about the generalization of this argument, so or like the machineries that take adopted today works in very generic setting, even Riemannian manifold, even graph, or a bunch of other possible settings. If you want to consider the more like the applied context, then this Laplacian can be replaced by the graph Laplacian, for example, and so on. So this can be apply in very, very different like the context also as well. But one thing I want to point it out is, so the key reason is that from the very last page of the talk today, so the key reason is that, so if you look at the very last page here, so you can actually realize that this argument does not need even real dimension 2. This is just a stochastic argument, so that you can even go to the infinite dimensional spaces. So it just uses the general, like the fact of the martingale, which is the Ito integral and also the stopping time. As long as you can make such a, like the framework, you can actually use this whenever you want. So that this can be generalized in very like a different context. But I want to point it out more like the specific context that I want to work some of you, not just a single one, but maybe eventually it could be multiple people here doing your own research. So why we need to care this alternative? So my own reason is slightly different. So again, now we can replace the maximum principle from this page. Then if you try to apply the maximum principle from geometric analysis point of view, then it uses so-called the Bokuno formula. Let me type out here. So I will ask some of you to present this formula very soon when we learn Riemannian geometry language. Bokuno formula. And if you apply this Bokuno formula, then you can see so-called Lich curvature play a role significantly. So for example, the generalization of the Schwarz lemma in the generic Kähler manifold also requires the Bokuno formula, truth be told, to control the Lich lower bound. So the Lich lower bound assumption in differential geometry is to apply the maximum principle. This is the only reason. So that without the maximum principle, we cannot produce the inequality. Then we cannot say anything, mathematically speaking. So this is the whole point. And we now know how to replace it. But the reason to replace the classical, like the geometry analysis argument to the stochastic argument is that, in fact, we don't even require the Lich lower bound, truth be told. So this is my real motivation to look at the stochastic argument again. So in order to establish the inequality, talk about establish the mathematical consequences, then we should establish the inequalities, basically. Then the maximum principle play a role. And even here you can see that we don't need to use the maximum principle because now we know the alternative. But the reason that I consider this alternative is that if you try to look at the Bokuno formula that you will see from this seminar for sure, is that you need to assume the Lich lower bound. But that can be even replaced. This is my reason. So, and I use this fact to write my own paper on the 4 years ago, and this can be done by using so-called coupling. So the coupling method can be used to replace the Bokuno formula in the very tricky and the clever way to claim much like the weakened setting with the stronger result. So that the coupling method is what I want some of you already studied this last year. And this is the technique that I would adapt to the Hedgens project this year. And maybe some point I might ask Andy to also learn this technique to claim more like the general, like the classes of Kähler manifold to establish the Schwarz lemma that is not known yet. So this is my key reason to consider this like the framework for graduate students. And I know some of you never heard the stochastic framework yet, but this is okay. So that we will also learn stochastic context from what? From the calculus point of view. So that you need to see how the elementary calculus really works one by one to get this like a new calculus. Then this new calculus is super powerful. So it can be adapted to the applied context and also pure like the mathematics research context, both of them. So, and this could be beneficial. This is what I aim for, do the research for each of you. But of course, it does not mean that you should apply the stochastic method as long as you are able to get something interesting. But this is one like the very interesting candidate of the alternative, and there should be the way to at least claim something new from out of it. So this is why I try to introduce this like the framework. So at least incoming fall, I don't assume we already established a decent like the background to produce some interesting results. So we still need to establish the like the necessary like the contents altogether. But there are two separate things that we will learn from the calculus point of view. One is the language, like the training of the Riemannian geometry. Another part is the stochastic computation that you feel comfortable with it. And so I can just explain that the language learning of Riemannian geometry requires the integration of differential form, basically speaking. And the stochastic part also requires the integration of stochastic differential form. So not rather than talk about the just the language like the framework abstractly, we will learn through the computation altogether. Then I will invite you to do it. So or contribute in some like the pieces of this computation together from this seminar. So that you will get the sense of. So for example, so as you can see that if you never saw the computation of the Poisson equation coming from the Gaussian curvature, you might not agree that from just a change in the coordinate, Gaussian curvature is a Laplacian or the Poisson equation. It's hard to admit it. But once you see the computation from either the S2 or the torus as we did today, then you can easily admit, yeah, that's the case. And there should be a more general framework like that. So that you first should just go over the computation without thinking that much. And once you click those like a computation, then you can see what was going on behind. Then you can see what are the certain like the benefits out of it. So it also works for the Wu's presentation later on. So I first let Wu to learn the modern technology of the PD side to solve the Poisson equation because this will be needed for sure. But eventually, all techniques I should not claim all, but most of the majority of the techniques can be replaced by the stochastic argument, and from there we can do something new. So that's my intention. So yeah, any other comments or questions? So one side, by the way, so I might force Hejin next week to give the presentation related to what today I explained, not the framework of knowing everything, but how the computation part of what Hejin is currently doing works in this like the like the generic like the framework. I will try to discuss Hejin in coming week to give some presentation of her own computation. And this is also, again, related to all of what you are doing. And I try to explain the spirit of how we catch up the knowledge of the modern and advanced level of mathematics rather than preparing the background, but just do the computation and then try to catch up what was going on. And by just looking at the penetrating examples with the depth of the computation, then you can really see the essence of what was going on there. And you can directly jump into the interesting research and you might if you're lucky enough, then you will get very interesting like the result. So this is a way to do the research, in my perspective. So yeah, any other comments or questions or concern? So there are two different separate themes of the presentations next week. One is I will force you to proceed the computation of Euler characteristic at least by using three complete different methods. Now you know what is the Gaussian curvature in the setting of the two-dimensional sphere and the real two-dimensional embedded torus in R3. After all, from this seminar, I will require all of you to know how to compute Gaussian curvature and Euler characteristic by 10 different methods. But for a moment, because you do not know the modern language yet, so I will just give you very elementary approaches, which is very beneficial to eventually get the intuition. So next week, I will ask you to present three different approaches of the computing Euler characteristic. But if it is important to establish the background for a moment, background in terms of the computation, this requires the integration of the differential form. So there are two options for U next week. Either you can go over entire series of the midterm of complex analysis. I'm talking about the entire problems, or you can do this computation. There are two options that you can take. You can do,
calculator. Yeah.
yeah, it's up to you. So,
Yeah.
and for hedging, so now we have the contents of the Monge-Ampere equation as we saw together, and we should see the context of the Hamilton-Jacobi-Bellman equation. So this is the context that we will also see from the computation. So those two are what I'd like to introduce, bring into this seminar. And after this will be all like the connected. So without me, so after you guys can also do the research with the collaborative like the effort together. It's completely up to you guys. And by the way, even Landon is today not here. So this is also related to the number theory and arithmetic dynamics, algebraic geometry research also as well. So those are all connected. So before we end the seminar, any comments or so type of the comments that I expect is so the way of doing the mathematical research might look quite different from what you expected for the first place. You might expect I first need to establish our necessary background, then it takes like maybe 2 to 3 years first, and then without establishing the background, we might not able to read the papers. It's not like that. Just look at the penetrating simplest possible examples first, and you understand what was going on by depth of the computation by yourself, and then you know what's the drawback of the current like the result, and you are able to attack from your again elementary calculus, and then you can later just study the framework what they use, and then you can try to replace some pieces of it, and you can this is something new that you like to contributed this place, and then you can just write your paper. This is the way to do the research. Um, so if there are no other comments, I'd like to ask Garen for your own comments. How do you feel? And also the potential presenters next week, especially Hajin and U, so that whether or not you're okay to get forced like this, or if you have any complaint, you can say so.
I'm enjoying these lectures. Yes. If you want to give me a topic, I can see how to present in that direction.
Yeah, that would be great if Karen, Dr. Children wants to present the isogeny graph with his own like expertise, then I will ask the participants here to reinterpret in terms of the understanding the maps between two different types of the torus. Then this could be good research in the machine learning direction also as well. And also this is a more like group theory oriented, but still this is good. Yeah, Karen, you can do that. Yeah,
Also,
Hajin.
please call me by my first name. No need, Chief Doctor.
I try to be polite, even I'm not thinking like that. So yeah, Hejin and Wu. So yeah, so please tell your opinions whether you're okay to present next week.
Um, I just do myself. Yeah, I try to do myself, do the best, and I will show what I'm doing now, and yeah, HJB equation. Yeah, I will show in next week.
Yeah, awesome. So of course we will try to discuss how we present and what do we need to drill together. So yeah, we'll discuss about it. And yeah, so is that okay with you to try to compute the Euler characteristic by either three different like the distinct methods, or just go over the midterm entirely? So I try to intentionally change the strategy of learning mathematics rather than just digest one by one, but just directly jump into the computation without knowing anything, and then you can catch up what was going on like that. So
Yeah.
So
Yeah. I'm gonna dive into Euler characteristic then. Yeah.
sounds good. All right, then, and this is the end of this presentation. So before we finish, so yeah, do you have any other comments regarding your presentation?
First of all, I'm sorry about the happening. Okay, and
That's fine.
and secondly, well, Well, I it is a very good opportunity to grab others' ideas and others others thinking. So let I hope th- uh, everyone get good chance. That's all.
Yeah, so as Take said, so Take asked to take the benefit for all of us. So I will also ask Loki at some point also present what he's also learning. So yeah, so this is the end of today's presentations. So thank you very
I
much
have
for contributing.
first thing I think if you want to if anyone to want to uh, study about the stochastic method, and then I will try to help. So contact uh, without any
Yeah, we will also do that together. I'm not saying that we should restrict to the seminar next week within two presentations. They can keep presenting what you wanna present. So even with like the short, like the amount of the presentation, that's okay. So by the way, Andy might not appear next week because his own like the own reason. So this is okay. So because we will post a record and also note into the Discord community so that we can like they discuss anything further. All right, so we will stop the record here.